Ranking molecules by their acidic strength or their basic strength or weakness is always tricky. It's always something that we have to put a lot of thought into. And we've been working on it since the fall quarter when we first learned our trick ARIO. ARIO we used to help us predict the stability of anything. So this was used to predict the stability. It could be literally of anything at all. And we used ARIO as a trick for helping us determine if a reaction, if an acid-base reaction was going to happen, or any type of reaction was going to happen. Because if our products were stable, if the things that we made in the reaction were stable, then the reaction was likely to proceed. Predicting stability is the same thing as predicting reactivity, which is the same thing as predicting acidity or basicity, because acidity and basicity are forms of reactivity. So something that is stable is not reactive. And if it is not reactive, that means that it would be a weak acid or a weak base, because acidity and basicity is just a type of reactivity. So when we're being asked a question like, which one of all of these is the weakest base, we're being asked which one of these bases is the most stable. That's all that this question is asking us. Which is the most stable? Which one is the least likely to act as a base? And a lot of times it's helpful when we're thinking about acids and bases. A lot of times it's helpful for us to think about what would the molecule look like if it acted like a base. If these were acting as bases, they would be getting protonated at their nitrogen. And this first one here I skipped intentionally because it has two nitrogens, which means we have two options. Could maybe draw it twice. It's not likely that it's going to protonate on both of those nitrogens at once. It's more likely that it will protonate on just one of them, one or the other. So those two options right there. So the question then is, which of these is the most stable? So the first thing that we should try to do in a question like this is see if we can refer to our tables of pKa's and pKb's and see if this is going to help us at all in any way. Like, do we have any of these guys at all in this set of four? We do have pyridine in our set, this molecule right here. It's got a pKa of 5.3. We also have pyrrole. Pyrrole has a pKa of 0.4. So let's go back and let's just start by copying those pKa's down. 0.4 for pyrrole and 5.3 for pyridine. 0.4 for pyrrole and 5.3 for pyridine. So these, I'm writing the pKa's. We'll put a box around them so that we don't lose them. And maybe before we get too far along in things, maybe we should remember what pKa, how it relates to strength. So if we have a high pKa, that means that we have increasing strength for a base. So if we're looking for the weakest base, then that means that we want the lowest pKa. So far, we can eliminate this guy because its pKa is higher. We're really just looking for, is there any way that anything has a pKa lower than 0.4? Let's go back to our tables again and see if we can find any more of these molecules. This one has got alkyl amines on it, and we have this guy right here, triethylamine, a pKa of 10.8. So let's put that back on the chart. 10.8 for this guy. So we also know, no for that. So we really have it, we've got it narrowed down to just these two right here. And unfortunately, this molecule, remember this is just two versions of the same molecule. This molecule is not in our data table, which means we're going to have to do a little critical thinking and try to figure out what's going on. So we have talked about this before, a phenomenon that we're seeing in this particular example, but you might not be connecting it to this concept. The molecule, the deprotonated molecule, this guy right here, this, you might not recognize right away, is an aromatic molecule. It has a total of 2, 4, 6 pi electrons. It has a conjugated system. Every atom in the ring is either part of a double bond or, like the nitrogen, has a lone pair on it, so that makes it aromatic. And when we protonate that aromatic molecule, it loses its continuous system of p orbitals. When we protonate the nitrogen, it's no longer even eligible to be aromatic, so this is a non-aromatic molecule. And that is why this molecule is so non-reactive, stable, and therefore the weakest base we've come across so far. It doesn't want to get protonated because when it gets protonated, it loses its aromaticity. So knowing that, just keeping that in the back of our head, when we go back to this scenario over here, we've got the exact same thing happening with this particular nitrogen. If this molecule, when it is deprotonated, let's take this stuff away, this molecule is also aromatic as it is right here because we have got 2, 4, 6 electrons in the pi system. So it is aromatic. And if we were to protonate this particular nitrogen right here, it would lose its aromaticity. So knowing that protonation at that nitrogen causes it to lose aromaticity, we can say that nitrogen is not even going to get protonated if it has another nitrogen that it could protonate. So it could protonate this nitrogen out here instead. That would not interfere with its aromaticity. And so that would be okay. Knowing that this particular molecule has an option for protonation that does not disrupt its aromaticity, it can get protonated and still be aromatic. That means that no situation, nothing is going to be worse than protonating this guy right here. No matter what, when we protonate that molecule, it loses its aromaticity. And because of that, that molecule, circled in blue, is definitely the weakest base. Out of all of them, it is the one that is least interested in getting protonated because there's no way to protonate it without taking away its aromaticity. And for all the rest of the molecules, it's a non-issue. So the next question on here, the next two questions on here actually, are asking about ranking or choosing the strongest acid, which is not in line with bases, but it's just a really good time of the year to review this type of stuff, and it's all using the same types of concepts. So ranking the strongest acid, again, whenever we can, we want to use the REO strategy. A, what's the atom with the negative charge? And does the atom like to have the negative charge? R, is there resonance? I, is there induction from any electronegative atoms nearby? And O, what's the orbital that has the atom with the charge? So when we're trying to figure out what's the strongest acid, what we're doing here is asking which one is the most reactive, which one is the most interested in reacting. And the way that we can tell that is which one of these gives us the most stable product. The most reactive molecule is going to give us a very stable product. So we want to think about, what does that product look like? If we're talking about reactivity as an acid, that means we're talking about getting rid of that proton and putting a negative charge on the oxygen. So when this question is asking us, which one of these is the strongest acid, you should be interpreting that as which one of these new structures is the most stable, which one of them is the best. And these are all really, really similar. It's going to be hard for us to use ARIO because it's a whole bunch of deprotonated carboxylic acids and they all look, really similar. Now, as you're looking at these structures, they may kind of give you flashbacks to the end of winter quarter when we were learning all the different reactions of aromatic compounds, orthoparadirecting, meta-directing, activating, deactivating, because these are substituted benzene rings. And so when you see these, hopefully that portion of your brain is getting kind of triggered. Like I remember, learning about these different substituents. That, even though we're not talking about aromatic reactions right now, your understanding of aromatic reactions is going to help you answer this question. The difference in all four of these molecules lies down here at the substituent that is attached to the ring. That's the only way these molecules are different from each other. And what we want to think about is, what do these substituents do for the ring? What can they offer or take from the ring? And I always want you to think about NO2 in its drawn out form like this. And so we did spend some time thinking about all of these different substituents. And one of the things that we talked about was, for example, if you had a lone pair of electrons on the atom that was directly attached to the ring, those lone pairs of electrons could move electron density into the ring. And moving electron density into this particular ring allows us to move electron density up and towards the COO minus group, which in this particular situation is bad. These substituents want to donate electron density and in our situation, we don't want electron donors because we already have too much electron density up here. We want something that's going to do the opposite, that's going to pull electron density away. So we don't want these electron donating substituents. That's not helpful at all. That's not going to help stabilize anything at all. The alkyl group is not an electron donor in terms of resonance, but alkyl groups, remember I always tell you to try to think about them like the opposite of electronegative, even though there's no such thing as that. We don't have a word for that. So alkyl groups, instead of being electronegative and pulling electron density towards them, they shove electron density away from them. So again, this is another bad substituent for this situation because it is pushing electron density towards that negative charge, which is no good at all. So just kind of by default, that means that this is the best, the strongest acid, the most stable acid, and we can also understand why. Because we have this negative formal charge or positive formal charge down here, we can actually move electron density down through this ring, and that positive charge is going to help stabilize it. So this NO2 group, because it is an electron withdrawing substituent, that means that it will stabilize the COO minus group. And it's only able to do that when it is in the para position or the meta position relative to the O minus. That was another thing that we saw. If it is in the wrong position on the ring, it's never going to get to be helpful at all. So last question, again, with acidity, this time we're not just looking for the strongest or the weakest. This time we're being asked to rank. So we have to be able to classify all of these. And again, we're being asked to rank in order of acidity. So that means the one that we find that is the most acidic is going to be the one that the product, so we're going to look at the product, is the most stable. So again, we want to think about what do these look like when they have been deprotonated. And hopefully we can use ARIO for this. We can't use A because the negative charge is on the oxygen for all of them, so that's not going to be helpful. R is resonance. Do we have resonance, yes or no? And for most of these, because we have this conjugated, we have the benzene ring, we are going to be able to move electrons down and around the ring. And maybe those resonance structures aren't going to be great, but they will exist. So because 3 out of the 4 have resonance, this guy that has no resonance is going to be the least acidic because its product is the least stable. And again, this is because there's no resonance. Of the remaining 3 that we have, so we've gone through R, I, induction. Let's see if we can use induction. Well, the stuff that we talked about up here might be helpful. We know that the chlorine is going to be pushing electron density towards the negative charge, which is a bad thing. And the NO2 group is going to help move electron density away from the negative charge, which is a good thing. The other molecule has nothing on it that can either move electron density in either direction. So it's getting no inductive effect at all. Nothing's happening at all. So it's not good, and it's also not bad. It's just somewhere in the middle. We can say that this one is definitely the most acidic because it is got the NO2 group that will withdraw electrons, electron density. So that's going to be a good thing. Of these 2, so both of them are trying to shove electron density up and in to the ring. However, with the chlorine, one of the things that we learned with the lone pair of electrons on the chlorine, we would be able to get additional resonance structures due to that lone pair of electrons adjacent to the ring. So this right here, this guy with the chlorine, is actually a little bit better just simply because it has more resonance structures to it. So if I call the most acidic number 1 and the least acidic number 4, I'm going to call this guy number 2 and this guy number 3, and both of them are pretty bleh. But number 2 is going to be number 2 because it has resonance, which is going to help to stabilize. And number 3 is number 3 because it doesn't have anything good and it doesn't have anything bad. It's just kind of in the middle.